Guy McPherson here again, and we're going to continue our discussion of deep time. And first, I would like to dedicate this session to a nationally recognized range scientist and former member of Texas Tech University's Department of Natural Resources Management, which is where I went to school. So I knew Carlton Moss Britton extremely well. He was awarded the Henry A. Wright Award for Lifetime Achievement in Fire Ecology, and that was on February 29th, 2012. He became emeritus from the Texas Tech faculty in 2008, and he received essentially every award that you could receive at the departmental, college, and university level when he was at Texas Tech University. Along with his wife, Becca, he established a scholarship for undergrad students at Texas Tech University. What I remember most about Carlton Britton, about Professor Britton, is that he had a bad leg. I don't know exactly what the deal was, but he had great difficulty walking, especially for extended periods of time. And yet he was out there conducting prescribed fires with all the graduate students, the occasional undergraduate student, and so on. We would be out there for 3 months almost every day of the year during the period between beginning of January and end of March. And he was out there with a bad leg, hardly able to walk, carrying a drip torch and giving people directions and instruction and continuing his life as an educator while carrying a drip torch. It was really quite impressive. So I'm pretty sure that Carlton Moss Britton has moved back to northeastern New Mexico from whence he came, because he talked about moving back there almost every day when I saw him. With that, let's continue our discussion about greenhouse gases causing climate change. And there are at least 31 greenhouse gases, but some of them are very poorly known, very poorly understood. So we're going to talk about some of the major ones today. With that, Neil, do you want to take over for a bit?
Sure. Thanks, Guy. And again, another very meaningful dedication there of a fellow mentor and climate biologist. We continue our review. When we say greenhouse gases, we're referring to these four groups, but as we'll see, there's many more. We've talked about carbon dioxide. Its sources are industries, transportation, deforestation, electric generation, coal burning. We've talked about methane in the previous session, and where it comes from and how it's emitted in great quantities in oil and gas operations. We're going to talk today about nitrous oxide and fluorinated and sulfur gases, among other things. And again, we're still scratching the surface. Greenhouse gases operate in the Earth's atmosphere by behaving differently than other air molecules. They tend to absorb the sun's heat as opposed to reflecting it back to outer space. They reflect it back to Earth, magnifying it. As we saw with a woman scientist named Foote, her experiment of taking CO2 gas in a jar versus normal air in a jar, identical thermometers in each jar, and placing them in the sun. You might think the laws of thermodynamics would mean that there's no way one jar could get hotter than the other. But it is the laws of thermodynamics that dictate that if there is a gas in there that is absorptive, it is going to absorb that solar radiation that is passing through the glass jar more than the air in the other jar that does not have this absorptive gas. And therefore, the environment inside that glass jar, you don't want to be in the glass jar that has the CO2 in it because you will be boiling. We get the same effect when we are in a car. And on a day when it's only 80 degrees out, if your car is sealed and the sunlight is shining in, it could get 90 or 95 degrees. This is not a violation of the second law of thermodynamics. It is the law of thermodynamics.
Absolutely. In fact, I, for years, referred to vehicles as greenhouses on wheels, because basically they act just like greenhouses do. The incoming radiation, some of it is held within the car. It can't escape because the long wave radiation can't get out through the windows. So It's not so much a car as it is a greenhouse on wheels.
These effects of these gases are non-controversial among scientists. They've been demonstrated, they have been proven chemically and biochemically and physically in earth science and in laboratories, as they say, both in vivo and in vitro. And here again, another diagram that includes and names carbon dioxide, methane, CFCs, chlorofluorocarbons, which many of which, not all of which, were banned by the Montreal Protocol because of their effect on the ozone layer, particularly at the poles. Ozone itself is a greenhouse gas. We say it's good if it's in the upper atmosphere. It's not so healthy if it's found in the lower atmosphere. We're not going to talk about ozone at length in this talk, and nitrous oxide, which we are going to talk about. Guy, before we go further, anything about greenhouse gases in general?
Well, I just want to point out that we are, even though these seem like long discussions, we are barely scratching the surface. With each one of these, we could spend weeks talking about each one of these greenhouse gases. So there's a lot more beneath the surface than we're going to go into here. And a large part of that has to do with the attention span of the typical folks who are paying attention. And it's a pretty small number with respect to attention span.
If you're dealing with people who have the attention of a goldfish, a way to say it is that CO2, carbon dioxide, has taken center stage as the star and the only star for many people. If they know about any other greenhouse gas, it's usually methane. And methane is poorly understood, in fact, by scientists and us. How it emits, how it operates in a cycle, both CO2 and methane are produced by life forms during their life and during their death. In other words, the cycle of life and death produces methane and carbon dioxide and some other greenhouse gases. But today we're going to talk about some that are only produced by humans, and which unfortunately have far more potent effects than either CO2 or methane. And we'll get to those. But first, nitrous oxide. So, yep, we began tracking nitrous oxide in the atmosphere around about 2000. And what has it done since then, Guy?
Well, as with these other greenhouse gases, and essentially every side effect of this set of living arrangements, it's gone exponential.
It's rocketing up.
It started out at 315
Yep.
parts per billion, and now it's up over 335 parts per billion. That's a significant increase.
And recessions don't seem to have an effect. We can actually see, at least with CO2 and methane, you can see a slight effect when we have a global recession. There is a little knock. It's just a slight ding. But I'm looking here at the year of 2008, 2010, which was the Great Recession. There was a recession in 2000, and there's been other sort of major planetary things like oh, that little kerfuffle we call the global pandemic in 2020 and 2021 doesn't seem to have had the slightest effect on nitrous oxide.
Nope.
But on CO2 and methane, those you can see those recessions in there. But as we know with recessions, the only thing that happens after a recession is the super wealthy take all the capital they've been safeguarding and they invest it and loan it to the rest of us, and we start partying again as a civilization. So we get back right on track after those knocks. I include this, and we'll be looking at this again. Guy, you're a scientist. You can probably explain this better. This is the wavelength and heating coefficients of these different gases. Would you take it from here? Because I'm not up for this. I don't know what I'm talking about enough.
Well, what we see here is the frequency on the horizontal axis and the absorption coefficient on the vertical axis. And you can see that it varies considerably for the different greenhouse gases. Starting on the left, water vapor, which is the most abundant greenhouse gas in the atmosphere. And then moving to the right just a little bit, there's carbon dioxide, CO2, shown that is currently, or according to this figure, at 420 parts per million. It's actually a little higher than that, but it's difficult to keep up given the rate of change of the greenhouse gases. Nitrous oxide is the green one shown about 3/4 of the way from left to right. And then water vapor makes an appearance again as well. And you can see methane down there towards the bottom. Not a great deal of methane in the atmosphere, but it has tremendous power with respect to greenhouse gas relative, for example, to carbon dioxide. And it indicates that there are significant differences among these handful of greenhouse gases that are shown here.
What I see, for example, that's interesting to me as a layperson here is H2O is very highly absorptive at this left-hand scale at the 200 and 400 level, but it's also highly absorptive. Am I reading this right? At 1400, 1600. Is that
Yes.
correct?
Yes, absolutely. So it's absorptive at two different places, two different sites, two different places on the curve there.
And some of these others are as well. If I'm looking, if green is just nitrous oxide, then it's absorptive up here at these high points. There's another sort of high point in here, and CO2 is very absorptive at this wavelength and minorly absorptive at these others. Am I reading
Right.
that right?
Yes, absolutely. And methane, CH4, shown there on the right, has a relatively narrow range of frequency.
Now,
But
the
it's
frequencies, am I right? All of this is energy. All of this is going to create heat and retain heat. If these gases are present, the work they're doing is retaining heat at these that is emitted by the sun at these wavelengths.
Yes, that's absolutely correct. So the sunlight comes in, strikes the surface of the planet, the ocean, or the terrestrial part of the planet, and heats those up. And the radiation that is emitted that comes off is a little bit longer wavelength, and some of that gets trapped by these greenhouse gases, just as within a greenhouse or your car when it's parked on a warm day. It's really hot inside compared to outside on a sunny day. So it's a similar kind of thing going on here.
Right. And I looked it up. If you look at a square meter that is held up to the sun just outside of our atmosphere, in other words, as the sun solar radiation hits the earth, if you were just above our atmosphere, it's 1350 or 1450 watts per square meter. That's literally 1400-watt bulbs that you could run on that energy if you captured it all. And a solar panel outside our environment would be it would be 6 times more powerful because at the ground level, at sea level, the watts per square meter, I think, are about 300 or 350. So what's happening is everything in the atmosphere is absorbing 1450 minus 350, 1100 watts is absorbed in the atmosphere. Some of that, would I be correct, Guy, is reflected, and that's a good thing for us. And
Yes, absolutely.
some of it is absorbed, and that is what is building heat.
That's right.
So it matters what I get out of this is it matters deeply what is the mix of gases in our atmosphere in terms of the behavior of warming or relatively more warming or relatively less warming or cooling of the planet. And that's just gases. We are not addressing particulates or aerosols here yet.
Yes, that's correct. And bear in mind that if it were not for these gases in this certain mix they have in our atmosphere, there would be no life on Earth.
It would
So,
be too cold. We'd be a slush ball.
right,
Mm.
exactly. So we have the greenhouse effect to thank, and because we have accelerated it to such a great degree, we have the greenhouse effect to curse.
Mm. So let's look at nitrous oxide because, again, the story of these they're minor players in terms of the media hype cycle, the Overton window, whatever you want to call it. We have a limited attention span and media span. And so a nitrous oxide is 300 times more potent a greenhouse gas than CO2 and has a long atmospheric life. It is produced by agricultural activities, particularly the application of nitrogen fertilizers. In other words, it's produced by a very prevalent activity. This is not some exotic refrigerant that we could ban, uh, as was the case with some of the refrigerants banned successfully in the Montreal Protocol. Nitrous oxide, I'm reading here, also emitted when fossil fuels are burned. So it's a basic byproduct of combustion. It's also a byproduct of nitric acid used for fertilizer and adipic acid used to make nylon and other synthetics. So all those synthetic fibers and wonder textiles that we rely on for everything now, not just what you wear, but used in industry, used in filters, used in all sorts of things, in fabrics, in covers, in plastics. They're all going to be releasing some nitrous oxide either in their manufacture or in their lifespan. And then domestic wastewater treatment also generates nitrous oxide. Anything you want to add on this, Guy?
Well, you indicated how important this particular greenhouse gas is, and I would challenge anybody to look around their house and not be able to find a source of nitrous oxide. It's one of these things that we don't think about very much. Doesn't come up in the news. Carbon dioxide is winning that game, but this stuff is everywhere. It's a as indicated, it's a very potent greenhouse gas, and we'd have a hard time holding together this set of living arrangements without it.
Indeed. I'm looking here at the pie chart here. Source EPA, fully three-fourths, 74%, 75% is agricultural soil management. This is the amendments to soil from nitrogen fertilizer, the manufacture of nitrogen fertilizer. It is also the turning of soil. Every time you plow, you're releasing not just nitrous oxide, but other chemicals, CO2 and methane. You are releasing that which is sunk in the soil. So the basics of agriculture involve unsinking sunk carbon and greenhouse gases. Am I
So,
correct?
yes, so if you eat, you're partially responsible for nitrous oxide in the atmosphere.
If you eat as a vegan,
Oh, yes, of course.
if you're just a vegan, I mean, I've had to explain that to the vegans that they are deforesting the Brazilian rainforest to grow soybeans. Some of those soybeans are used for cattle feed, but the vegans are not eating cattle, they're eating soy milk. And the demand for soy milk in North America and Europe by the vegans is so great that, yes, Brazilians are plowing under the rainforest to create soy for the vegans. It is
And
absolutely the case.
palm oil,
And
anybody?
palm oil, yes. Because if you're going to go vegan, you're going to need and want food that has so many different vegetable products and textures in it that the industry is quite happy. Agribusiness is quite happy to cater to the vegetarians and vegans by providing magnificently processed oils and carbohydrates in the forms that you vegans find acceptable and force feeding them to you. They love that. They love that you love those things. They'll just grow more.
Right.
Manure management. So part of agriculture would be manure, but it's called out separately here. That would be animal waste. And the vegans, it's very hard to find corn or vegetables. If you go to your organic store as a vegan and say, I only want to eat vegetables that have been grown without animal manure, if they are being honest with you, they're going to have to say, well, you can't have any of the vegetables here, honey. You're going to have to go find the mythical vegetables that are not grown without any form of manure, not chicken excrement, not cow excrement, no excrement from any life form. And guess what? It's very hard actually to grow many things without animal manure. Am I correct in these statements?
Absolutely. Yeah,
So,
it's all interconnected, and Big Ag has ensured that there is essentially one way to do everything, at least in the interior part of this country. And so that's what we do. And
Indeed.
try to break outside of that mold and do it a different way is going to be very challenging.
I'm going to move quickly here. This is just another set of charts that shows the last, since 1980, nitrous oxide from fossil fuel, nitrous oxide from industry. It's funny that that kind of goes down and then is level, from waste and wastewater, and from biomass burning. Again, when we create a biomass plant, a lot of people are thinking that biomass incinerators to generate energy, to turn a turbine, to generate electricity, are better than a generator powered by natural gas or coal. I think the results are in. It is no better in terms of greenhouse gases that affect the climate. Burning trees or biomass sounds better because it isn't oil, it isn't coal, but I think the results are in. It's contributing greenhouse gases as well.
Absolutely. This is biomass burning. That's cutting down the forest to make sure you don't burn so many fossil fuels. So it's cutting down contemporary forests so you don't have to burn old forests in the form of coal.
I found this chart from EPA, and it's a very nice chart because it's got graphics and things, and it's tracking three gases here: nitrous oxide, which we're talking about, carbon dioxide, and methane, which we talked about in previous sessions. And what it says here is the soil management is the biggest arrow here, and it's maroon colored for nitrous oxide, 292,600 kilotons. Um, Converting land to cropland. So again, cutting it down and making it into a monoculture. The energy that is consumed on the farm creates carbon dioxide. That's the blue. And then over here, I was surprised that it is less. The arrow here for methane, 170,000 kilotons. I mean, there's still a lot of methane coming out of those cows' butts and mouths. It comes out of both ends, I think. And manure management, which we've talked about. Rice cultivation also yields methane. But it is not simply the case that farming produces bad methane from animals and everything else about farming and growing crops is neutral or healthy or organic or crunchy or granola. Is it, Guy?
And absolutely not. There are consequences associated with our actions, and when those actions mean more than 8 billion people, we're talking about a lot of consequences.
And the greenhouse gases from farming are, just in my research as a layperson, are proving to be a lot more complex, varied, multiple, larger, and more nuanced than is represented when I hear someone who obviously has an axe to grind against animal farming talks about non-animal agriculture as if it is a glowingly healthy thing for the planet, the way we do it. And I happen to know that it's not, and I've done the research, and the more research I do leads me to believe that we're being misled in all directions about these things. Do you feel the same way?
You should stop doing research then.
I should stop doing research. It's too bad. I was taught to be a critical thinker, Guy. Please feel mournful sympathy for me.
Yes, absolutely. Critical thinking in this society, it's a lonely experience.
It is. And then I find this from Cicero, which is the Center for Climate Research of the Norwegians. And the Norwegians actually, I don't know if they've done the data gathering, but they have published 2,000 years worth of nitrous oxide data, again, from the our Antarctic and Cape Grim ice core samples. So just in case you wanted to believe that nitrous oxide has been rocketing up the whole time, here to dispel that is the group Cicero from Norway that will show you that we really rocketed up nitrous oxide starting when? About 1850, 1860, Remind me, Guy, what did we start then? What age of production did we start then?
Well, we generally put the Industrial Revolution at 1750, plus or minus a few years. But according to James Hansen, in many presentations, interviews, and so on, we only add about zero point 0.2 degrees between 1750 and 1850. So you can see that this thing really skyrocketing in about 1800 or 1850. And so things had started to warm up on the planet at that point. But holy cow, things get pretty much out of control after that, don't they?
It really looks like it coincides with the oil age, which inaugurates about 1850. The coal age was already underway. But what a rocketing up we see. The two start working together, oil and coal, for a century. And what an effect we see there. I don't think there's any way to make a case that nitrous oxide is rocketing up because Mother Nature suddenly decided to let out a big fart of natural sources starting in 1850. When you have 1,000 years, 2,000 years of ice core data showing relatively stable levels, you don't have to be much of a scientist to see what's going on and to connect it with human activities.
Right. You look at that first 1800 years, and there's just slight variation from roughly 2000 years ago up until 1800, maybe going from 260 to 275 parts per billion of nitrous oxide. And then we hit the jackpot with around 1800, the thing skyrockets up. And by the time we get to 1900, it's all red line. We're redlining nitrous oxide in the atmosphere.
Right. Let's keep going with this. Again, from Cicero, showing us where the sources are in their research. Direct nitrous oxide from agriculture, from others, nitrogen additions, I guess, and from climate and CO2 and land use.
But most of this is agriculture.
Most of it is.
And that's huge. So again, if you want to eat, then nitrous oxide is us.
If you want to eat plants, mainly. I mean, nitrous oxide is not coming from animal agriculture as much.
Right.
It's coming from plants. Now, yes, if you raise livestock using hard seeds that you've grown in a field, then yes. But as regenerative farmers and ranchers know, you do not have to feed. In fact, you should not feed livestock a lot of solid, hard monoculture starch grains. That's not what they ate. They ate wild perennial grasses. Yes, those grasses had seed on them at some parts of the year. So would not be truthful to say they never ate seed, but they did not eat finished grain of the kind that we feed them now that fattens them up. It's not suited to them. They're not healthy when they eat that much grain. They have to be kept alive by antibiotics and steroids, and it's not healthy meat. Am I on the right track with that?
Absolutely.
And so what this nitrous oxide revelation is the real downside of row crop, monocrop agriculture the way we do it, with lots of soil amendments and techno fertilizers and chemicals. This is not the kind of agriculture that my permaculture friends do. They do not turn the soil. They do not add fertilizers other than the manure from the pasture-raised chickens and other animals, usually smaller animals that they have. And I haven't seen a measurement of what nitrous oxide is produced from a true permaculture or regenerative farm, but I suspect it is less. Would I be crazy in that assumption?
I suspect it is considerably less. And permaculture is a revolution. It is a way of looking at and managing your own life and land. And so it is completely different than the kind of agriculture we've been talking about so far. Is it capable of supporting more than 8 billion people? Probably not. And certainly not if we're going to make billionaires out of a few of those people.
I've said in the past, the Haber-Bosch process, which is a German scientist in the 1910s or so, invents a chemical process for creating elements of fertilizer that are critical. That is part of a revolution, a green revolution, and a food productivity revolution that, of course, we celebrate because it enabled the feeding of so many more people. But it enabled the population to go from a billion to 8.5 billion. That means about 6 billion people are what you would have to call Haber-Bosch people. The nitrogen and carbon in their bodies is there because of a chemical process that was invented in 1910, 1920. And without that process, we would have fewer people because we would have less food able to be grown, less bio-intensive farming. Am I correct about that?
You're right on, exactly. Had it not been for the Haber-Bosch process and its implementation, specifically for ammonium fertilizer, if instead we had put that infrastructure post-World War II into permaculture, for example, into retaining water instead of just explosively putting water onto all the soil that was used to grow plants, we would have a completely different life.
And a smaller population in the planet, naturally,
Yeah,
and not as much pressure, considerably less pressure on the resources and tolerances and boundaries of this planet.
yes. It'd be a completely different world, and I suspect a lot better world.
Here is one of our nice little charts showing what we need to do to get to the proper nitrous oxide budget. This is from the Global Carbon Project. And yes, there's no carbon in nitrous oxide, but they're tracking that because it is a recognized greenhouse gas. And so this is to help us figure out how we can cut back to achieve the budget of that will reduce this greenhouse gas and stop the abrupt heating. I'm not going to go through this. You can look at it as your leisure. But from right to left, you see that with nitrous oxide, there are atmospheric cycles that do bring it back as a sink from rain and from sedimentation from the atmosphere. It falls out, but it's being generated in natural sources in the green from oceans and land and other fluxes that we've seen. And the anthropogenic sources are nicely identified over here. We've already reviewed them. It would be nice if we could cut back on all of those, but that means cutting back on agriculture, the treatment of our wastes, biomass burning, which I'm sure we could cut back on that because that was always a stupid plan as a substitute fuel. But the fossil fuel industry, we'd have to cut back on that as well, or somehow magically scrub all of the emissions of nitrous oxide. Any thoughts on this, Guy?
Everything that you are pointing out here indicates what a great challenge we face. If we are able to reduce these orange bars on the left of the screen, what are the consequences going to be? Have we thought about that? Have we thought far enough ahead? So how many people are going to have to die if we're going to reduce those orange bars, cut them in half, cut them by 3/4, right?
I think that what's happening is reactive things like the Netherlands, where they've ordered the farmers who are some of the most productive farmers in Europe. In other words, the Dutch farmers produce more calories in our food system per unit of added fertilizer, per unit of soil, by any measure than almost any other farmers in Europe and maybe in the world. I think the Japanese and the Americans come close, but they've been ordered for the last 5 years to drastically reduce the amount of fertilizers and other things that they're adding to the soil. And the result, and they've been ordered to do so at a draconian level, a level that when I look into it, I'm like, no farmer could adjust to that. There probably was some other way to start them on a track to reduce it and incent them. The result is that the Netherlands has a growing right-wing movement. I wonder why. And this is an example where I get very frustrated with certain environmental things, Guy, because they literally just inflame people in the wrong way. And it's just been handled very poorly in the Netherlands. I don't know if you have been tracking it, but you've seen this kind of thing elsewhere. What are your thoughts?
Well, we've grown up in a certain way. We are fully embedded into a certain set of living arrangements. And by the time we notice the danger signs, the actions that we would need to take are probably not even possible. And so what do we have in response? One of the things you mentioned was this extreme right-wingism that has developed in the Netherlands. But that's just scratching the surface. There's all kinds of responses, most of them negative, when we try to change all that we have ever known, right?
And impose it suddenly impose a change on people, usually with no explanation or an improper explanation. And sometimes we make mistakes. The whole diesel thing, we'll talk about that later. The French had a massive spasm of protest for lasted almost 2.5 years from the yellow jerseys, the gilets jaunes, because they suddenly, after incenting diesel use for 30 years, they suddenly said, well, diesel is now bad and you have to pay, I think, 5 cents more for diesel. And that was it. People just broke. They'd reached their limit. And the result in France was 2.5 years of protests. And still, those people are now fully sensitized to ham-handed and wrong-headed approaches to ordering them to change their lives. And I think we're going to see more of that kind of reaction. And I can't morally condemn it, because what are these people to do? What's your emotion around all of that?
Exactly. What are they to do? What are we to do? We grew up with a certain set of living arrangements. Now you're going to take some of that away. We grew up with certain privileges. That's all we've ever known. And now you're going to take those privileges away. We grew up expecting that when you go down the stairs, there's always an 8-inch rise. If you change that, people start falling over. They start falling down the stairs. And that's what we're talking about here at a much, much greater level than just simply going up and down the stairs. I mean, this is the whole set of living arrangements that we grew up in, and you're going to change the tricks now?
And so I'm sort of find myself often advertising caution to environmental activists, because some of what they indicate they want done or want to do, I say, if you even succeed in getting a legislature or a leader, whether at the state level or the federal level, in any country, most countries have this distinction between states and federal. If you get your agenda done, it'll last one term, because that politician will be thrown out one way or another, and it might actually create a spasm of real craziness in the population, and you don't want that. Is there another way? Explore all other ways rather than legislation, force, mandate, requirement, whatever, please, because it's just going to lead to more right-wing populism.
And we got enough of that already. Thank you very much.
So now we get to a category. It's not my name. It's been named as the Immortals. And there's a very dark reason why they're called the Immortals. Sulfur hexafluoride, SF6, hexafluoromethane, C2F6, tetrafluoroethane. There will be a quiz, Guy. There'll be a midterm at the end of this thing with the chemical structures and names of these horrible chemicals.
Yeah, these are some insane names. Nobody can keep track, of course, and they're called Immortals for a reason. They last a really, really long time.
And so this was a revelation to me, and you'll just have to excuse. I think for many in our audience, this will be new. So excuse if we do a little more just reading from slides, which I know is like watching the grass grow. U.S. emissions of the world's most potent greenhouse gas. Did you hear me? The world's most potent greenhouse gas, SF6, are 56% higher than EPA estimates, a new study shows. Electric utilities are responsible for the nation's higher than expected emissions of sulfur hexafluoride. Who knew? How the hell is sulfur hexafluoride used by electric utilities? We will find out.
I'm guessing nobody watching or listening has heard of sulfur hexafluoride until now, much less that it's 25,000 times worse for the climate than carbon dioxide.
Indeed. And so, realize that means you must pay attention to it, even if by volume it is one it would have to be 1/25,000th the volume of CO2 just to be on equal footing with it. But even then it wouldn't be, because it lasts for 3,200 years in the atmosphere. It would only be on equal footing with if it was 1/25,000th the emission by volume, and it only lasted 1 year in the atmosphere, you might say, well, it's on equal footing with CO2, but it lasts 3,200 years. It is a man-made gas. I'm reading in the middle section. A man-made gas used by electric utilities to quickly interrupt the flow of electricity in high voltage circuit breakers. It is also the most potent greenhouse gas ever studied by the IPCC. So this is not a gas that is created when you plug in your toaster in your home, or your fan, or your vacuum cleaner. It is a gas that is used in electric utilities in large volumes to fill chambers around giant electric transformers and circuits to prevent arcing, which would bring down the grid. There's another way to say it. It would bring down the transformer system, the substation. If arcing occurred, it would make it impossible to regulate the voltage, and would burn out and fry equipment. Am I correct in this?
And all we ever hear recently, within the last couple of years, we need to go electric on everything.
We do. We must. It will save us gasoline. But yet the electric power grid for generation, distribution, and transmission uses this gas as a ideal gas to prevent arcing. It's used in the power grid in insulation, for arc quenching technologies, for transmission and distribution. It's also used, if I'm reading now on the right hand in the blue, by the semiconductor manufacture industry. I think for the same thing. If you're making a microcircuit, you need a chamber filled with this stuff so that tiny little sparks and arcs don't fry your microelectronic components. It's also produced in the making of aluminum, the smelting and making of aluminum into the shapes that we need, and the processing of magnesium as a metal and as a mineral, and several other industrial activities. I don't believe it is regulated by the EPA. I think it is monitored, but it is not regulated. There's no limits set for its use. Please check on that. If I'm wrong, I'll take it back, but I think many of these other things are not regulated by the EPA. Now, of course, thankfully, we've been measuring it since about 1997, sulfur hexafluoride concentration in the atmosphere. And Guy, recessions, great financial crises, pandemics, do you see even a slight bobble in the rocketing up of sulfur hexafluoride?
Nothing. Nothing. For all practical purposes, it's straight up. That is a very smooth curve.
So we haven't made a dent in it with even a massive reduction in our behaviors during those three events. The dot-com bust, the great financial crisis, and the pandemic are all on this calendar here in front of us.
And it's tripled in what looks like from 1994 to current, for all practical purposes. Tripled.
It's tripled. And what I'm not clear about is the arc quenching in the electric utility industry. It should be captive. I mean, but somehow they're releasing the gas, and I don't know what the conditions of that they release it into the atmosphere. I don't know whether it's possible to make them keep it captive. I don't know if there's a technology. Somehow it's getting released, obviously, on a very steady basis here.
Right.
It's terrifying. So this introduces, because this is the first of several gases that are in the category labeled the Immortals. So I'm just going to read here again because we need this tutorial. Human-made compounds, which include tetrafluoromethane and hexafluoroethane, as well as we were just talking about sulfur hexafluoride, are some of the most potent and longest-lasting greenhouse gases on the planet. Tetrafluoromethane, a byproduct of aluminum manufacturing, is the longest lived of all. It has an atmospheric lifetime of 50,000 years, not 3,200. It is a Methuselah that lasts 50,000 years. That's forever. The chemicals share the same fluorine-based chemistry as per- and polyfluoroalkyl PFAS substances, the toxic forever chemicals linked to cancer that are used in everything from non-stick coating on pots and pans to fast food packaging, water repellent clothing, as cosmetics. They're also used in a variety of packaging. And there was people may remember the butter manufacturer, Kelly Gold, had to change their packaging because it had PFAS or PTFE in it. These are all related, and they're fabulous chemicals in terms of their performance. But if they make it into the climate or into our bodies, they are not fabulous. They are the opposite of fabulous. Ranajit Sahu, an independent environmental consultant and engineer, said the chemicals had, quote, a few decades of great use, and then the after effects started to be felt, end quote. Guy, I mean, isn't that the case? A few decades of great use, and then we said, oops.
That's the human story right there.
It really is.
At least during the Industrial Revolution.
Quote, first we had ozone depletion, then PFAS contamination, now climate change, all from the same carbon fluorine chemistry, Sahu said. It's tragic. It is almost like a Greek chorus is in the wings saying, this is your destiny as a tragic hero, that which you wield as a strength, that sword of technology that you wield cuts both ways. And you haven't even realized that you've cut your own foot off with it until you try and take the next step. Global emissions of these long-lived F gases, we won't say that they deserve the F word, in 2018 equaled the climate impact of 264 million tons of carbon dioxide. Huh? 264 million tons of carbon dioxide, based on Inside Climate News assessment. This hasn't been talked about enough, Guy.
No, absolutely not.
Did you know this?
No, of course
in this
not.
detail.
Are you
didn't know this?
kidding? Nobody knows this stuff. It's inconceivable that any one person could keep track of a quarter of what we talked about so far.
And even in science, even in established science, certain things are popular. If I wrote a grant and said I wanted $100,000, if I had the credentials and were a professor of climate geochemistry, and I said, I'm interested in this new problem, I want a $100,000 grant to buy some sensors and send some people out and do some measurements in some industries that are emitting these, what would be the likelihood that I'd get a grant? It's not popular, am I right? No one's heard of it.
No, it's essentially zero.
So I might not get a grant to study this because people would say, well, why aren't you studying CO2 or methane? Those are much more prevalent. That's if the electric power industry isn't already in the hold of, these universities. We'll see.
One of the interviews I did within the last few months was about PFAS, these forever chemicals. And they were essentially unknown to the hosts who were asking about them. And that's because we don't know anything about them, right? Everybody knows about carbon dioxide because it's in the news every 5 minutes. But has anybody heard of forever chemicals, these PFAS chemicals? No, of course not.
They also get called pollutants. They get called pollutants, but they are greenhouse gases. And in fact, they're much more dangerous in some sense. They are distinct from CO2. And I find them, in my own way of thinking about them, is these are high-tech chemicals. They are not like CO2 and methane, which are basic to the respiration, life cycle and decay of life on Earth. None of what we are now talking about in this section are even produced or natural in any cycle or sink. These are ultra high-tech, human-produced, specialized, miracle chemicals. Am I right to see that distinction, Guy?
Absolutely.
And here is a chart. These are just charts to help us visualize. We have CO2, which is a relative longevity of atmospheric gas concentrations. People may be surprised to see that CO2 itself is rated at 300 to 1,000 years. Sulfur hexafluoride is 3,200 years. Hexafluoroethane is 10,000 years, and tetrafluoromethane is 50,000 years in the climate. There is nothing that would degrade it or bring it down or chemically change it in the atmosphere. Many of the other ones that we know of, ozone can be broken down quicker than these nightmarish Dracula vampire type chemicals in our climate. Another chart just to show the tiny dot, this tiny little blue dot at the top, CO2, and its relative global warming potential over 100 years. The next largest is the giant yellow circle of tetrafluoromethane. Its warming potential of the same volume is 100 times at least as CO2, and then hexafluoroethane and sulfur hexafluoride far greater in the warming potential over a 100-year period. Again, this is just trying to get us to visualize it and understand it.
50,000 years ago, 50,000 years ago, that's what we're talking about here. Humans had just come out of Africa. Neanderthals still existed. It was a completely different world 50,000 years ago. And for something to last 50,000 years in the atmosphere, and to even think about what the human condition would be like at that point, boggles the mind.
And that it is warming the planet. It's not a form of warming that would change with stopping emitting it for 50,000 years. The way CO2 would change if you stopped emitting it or decreased it drastically, it would take between 10 and 40 years for a reduction to be visible, but it would be visible. This stuff is just up there. And it also makes me think of the half-life on nuclear power. The half-life of the longest isotope that is very dangerous in our conventional approach to nuclear, which produces these radioactive isotopes, not thorium, which would be a smarter form of nuclear, which was thought of but rejected because it wouldn't yield weapons grade uranium and plutonium. But the half-life of the longest components that we need to be careful of in a nuclear power plant is 30,000 years. That's less than 50,000 years. So from that time scale, we will, if we tried to think in the future of how long we're going to have to monitor our nuclear power plants, even if we shut them down as safely, which may not be possible, that's 30,000 years. This is 50,000 years. Am I right to see the drama in that comparison?
Oh, it's unbelievable. We as humans, we can't even imagine 50,000 years, what that's like. We can barely manage what's going on in another 5 hours.
Some of us only plan as far as the next Super Bowl. I mean,
right.
What tailgate party are we going to throw?
Yeah.
And which type of tailgate accessories are we going to buy? So quickly, SF6 other uses. And here's the fun stuff. Speaking of sports, in the early 1990s, SF6 was widely used as the air in race car tires, in tennis balls, and Nike Air shoes. It is a larger molecule, and it literally keeps those things inflated for longer and doesn't leak out the way conventional air would, just normal room air. Refrigeration and air conditioning companies adopted fluorine-based chemicals as an environmentally friendly alternative to the banned chlorofluorocarbons, chlorinated chemicals that were destroying the atmospheric ozone, which were banned by the Montreal Protocol in 1987. The synthetic fluorine compounds were odorless, colorless, non-toxic, non-flammable, and incredibly durable. They didn't harm the ozone layer, and in the case of SF6, its large molecular size meant it wouldn't easily leak. So when they dig it all up, they'll find that they'll still find our tennis balls, the air in our Nike Air shoes, and our race car tires are still good, but the atmosphere is ruined by by these things.
Yes, we won't be able to survive, but there will be evidence that we were once taking things like Nike shoes very seriously.
I'll say, what a party this species had. We now come to the final one that we're going to discuss today, which is black carbon. And again, I wasn't aware of this. I mean, it's pretty commonplace once you read about it, but what its role is. So black carbon is one of the main components of soot, smoke, and smog. If you make a fire, in your fireplace, you're going to have black carbon. It is a product of the incomplete combustion or burning of organic materials. We've talked about combustion. And now, if you're going to burn a fossil fuel, it seems to be generally important that you combust it as efficiently and completely as possible. You don't want to waste it, and you don't want to emit it uncombusted into the atmosphere. The combustion products are bad enough, but uncombusted apparently is worse if you've released it. Before the industrial age, fire was the main source of black carbon, whether naturally occurring or human induced. As part of the natural carbon cycle, the burning of biomass produces more solid black carbon, or biochar, than it produces airborne black carbon soot. So fires on the ground, as in even before humankind, fires start in forests and forests burn. And of course, some of that is airborne as soot, but some of it is burned efficiently enough to just remain as biochar, which actually sinks carbon. It has to burn anaerobically, am I correct? Or almost anaerobically to be a good form of biochar. Is that correct, Guy?
Yes, yes. In fact, I created a system to create biochar when I was living off grid in New Mexico. And you have to get as much air out of the system as you can and burn it so that it turns to charcoal without combusting very much of the material. That's why it's important to keep the air out.
Right. And so soot fire, the burning of wood for wood fires for cooking in the third world, produces a ton of this stuff. And it would be much better for those people to get a hold of what's called a rocket stove, which burns much more efficiently and fully and creates a lot more heat for a lot less fuel because it is burning that fuel super efficiently and completely, or to give them a well-made small gas burner. And people don't like it when I say, but it would be much better for the climate to substitute bottled natural gas. Yes, you heard me right, ladies and gentlemen. Bottled natural gas for wood fires in much of the third world, and healthier for the lungs of the mostly women and children that are confined in shanties around these wood cook stoves. Am I on the right track, or am I telling a lie?
You're on the right track, sadly.
Sadly, 40% of the soil's organic carbon is black carbon, which increases the soil's fertility, as biochar is like small amounts of black carbon. But biochar is used to increase the fertility of soil degraded by intensive industrial agriculture. So it's good in the right place.
Yes, absolutely. And in fact, post-World War II, had we gone the route of biochar instead of going the route of fossil fuel laden fertilizers, we would have a very different world. For one thing, you only need to apply the biochar once every 100 years or so, instead of with ammonia fertilizer, which you apply once or twice a year.
I don't think you can get rich as an agribusiness if I teach you how to make a biochar, or if I make the biochar and sell it conveniently to you. I'm probably not going to get as rich as if I sell you Haber-Bosch fertilizer and nitrogen and potash that I've dug up out of the planet.
So you're telling me it's about the money?
I think it's about the money, Guy. I'm afraid that you're right.
Hmm.
Industrialization, beginning in the late 18th century, coal, the dirtiest fossil fuel, replaced biofuels, meaning wood, as the primary source of black carbon. Atmospheric black carbon increased sevenfold, peaking in the early 20th century. So that London smog and fog from coal. The burning of biomass has continued, however, especially in rural areas of low-income countries where 2 billion people rely on biomass in the form of wood, dung, or crop residues as their primary fuel. This is what we've been talking about. On a global scale, fossil fuels are the source of black carbon emissions, which contribute. The contribution varies depending on the degree of industrialization, urbanization, with biomass contributing more black carbon in rural regions, and fossil fuel burning, the burning of oil and gas and coal, contributes more in urban areas. Diesel exhaust emits more black carbon than any other single source. It always mystified me, even back during the oil crises of the 70s, Guy, because I could visually see that every diesel vehicle issued horrendously unhealthy black soot and smoke. And yet we were told diesel's better than gasoline. Am I imagining this, or is this what we were told?
If you were imagining it, then I was imagining it too.
Never understood it. And then when the French suddenly 6 years ago said, "Oh, diesel's bad," I was like, "It took you this long to figure it out?" So I won't read all of this, but I will read in the section here, black carbon in bold, has been identified as the second most important source of greenhouse gas emissions. That's a news item that did not make it, if that is true. And I should cite where I forget where I took this from, but it's from some publicly available analyst report. Black carbon from fossil fuel sources have twice the global warming potential as black carbon from biomass sources. Interesting. Because black carbon absorbs rather than reflects light, it prevents energy that would normally escape back into space from leaving the Earth's atmosphere. This is the case whether the black carbon falls back to Earth's surface or is suspended in the atmosphere. So I guess it's not one of the good aerosols in most forms.
No.
No, it is a warming aerosol. According to recent research, black carbon is responsible for more, I'm reading at the bottom right, more than 50% of accelerating glacial and snow melt. And so the black carbon that settles now on the ice caps especially in Greenland and what's left of Antarctica, is increasing the albedo and causing faster melt and heating.
Decreasing the albedo.
Decreasing the albedo, right.
And that's right. It doesn't take a lot of black carbon on the surface to cause a very rapid rate of melting compared to if you don't have that black carbon there.
And if there's less frequent snowfall, if in the older days, if there was black carbon settling, there always has been in industry. For the last 150, 200 years, there's been black carbon settling on ice. But if there's a much lower rate of snowfall that would cover every layer of black carbon, then its effect is multiplying. Am I correct in that?
Yes, absolutely.
I grew up in a northeastern city, and
the snow would get dirty, but if the snowfall was frequent, new snow would fall and cover over the dirty snow, and it wouldn't melt as fast. And I think I was noticing this very process even just in an inner city.
Yes, absolutely. I grew up in a place in northern Idaho where it snowed a lot, and once there were a few inches of snow on the ground, we would not see the ground for another 3 or 4 months. It just accumulated and kept going, kept going. So even if there was some dark matter that covered the surface for a short period of time, didn't last long.
Right. And the new snow neutralized the effect of the pollution settling on the older snow.
Absolutely.
If you go back to your hometown during winter, Guy, have you noticed a change in the winter?
Why would I do that? It's pretty interesting. I did go back a few years ago, and the changes were profound. It was a timber town when I was a kid. There were 3 large sawmills in a town with a population of about 700 people, and the population is down to 440 people, and all the timber's gone, of course, and it's a meth lab for all practical purposes.
Basically, the economic base is gone, and people are in a desperate way resorting to such things as meth and synthesizing drugs from agricultural chemicals. That's horrible.
Horrible. Yeah. Absolutely. It wasn't the people's fault. We got trapped in it.
We have almost reached the end. We're on this black carbon thing. Unlike greenhouse gases, black carbon is a climate forcer you can see and feel. 2/3 of the black carbon in the Arctic comes from heavy fuel oil, the byproduct of bunker oil used in shipping. And that bunker oil is now subject to a requirement that it not have sulfur in it. But I don't know whether the new rules are going to lower the amount of black carbon. What do you think, Guy?
I have no idea. And given what happened in the Atlantic Ocean with the new rules reducing the amount of bunker fuel that's used and therefore causing significant warming of the Atlantic Ocean and surrounding areas, maybe people are going to look twice at this and go, the only thing worse than putting greenhouse gases into the atmosphere is not putting greenhouse gases into the atmosphere, because what comes with those greenhouse gases are the aerosols that block the incoming sunlight.
Right. Crazily enough, the actions of we humans in burning all this stuff contributes both warming and cooling, because the greenhouse gases contribute the warming, but some of the particulates that we put up and some of the aerosols contribute cooling. It could be that those were in balance and we saw moderate heating, even though the volume of greenhouse gases was going up, the volume of aerosols was going up. So crazily enough, our activities resulted in heating, but less aggressive heating. If we then clean up just one of those two things, the aerosols, you're saying that we might see faster heating all of a sudden with the same volume. And of course, it's never the same volume of greenhouse gas. We're always increasing that. But for a given volume, it will be more heat producing.
Absolutely. And that's something that's only been reported relatively recently. I refer to it as the best kept secret in climate science. There's peer-reviewed literature going back to 1929 indicating the aerosol masking effect and its tremendous power. It's starting to receive a lot more attention recently than it had for a really long time.
It's like scientific nuances that sometimes scientists refuse to try and explain to the media or to anybody because it's either too complicated and the scientist is lazy. Explaining stuff is challenging. I find it challenging just to even talk about this stuff intelligently based on what little I know. And scientists sometimes feel like, well, the public's not going to get it, so I better keep it simple. I know that's a temptation, but in the case of these climate-related things, I don't think it's helpful.
Right.
We have to take the time and explain the nuance to people, and then try and explain intelligent policy and legislation that might have the right effect. That's a big challenge.
It certainly is.
Black carbon impacts climate in a number of ways, some of which scientists are still trying to understand. Yeah, you bet. Its impact depends on where the black carbon is. In the atmosphere and on the snow and ice, it absorbs sunlight. We've said that. Well, while it's airborne, black carbon can interact with clouds in various ways. Sometimes it causes clouds to evaporate, which leads to further warming, but sometimes it helps clouds form, which can help to block incoming sunlight and cool the planet. So it's interacting with water vapor, that other major climate gas. What does this say to you, Guy?
Again, it's complicated.
Mm.
It's doing multiple things at once. And we never have the full picture, obviously. But if we did have the full picture, we would be able to determine where it was doing us good and where it was doing us bad. And unfortunately, I don't think, given the complex and complicated systems that we're working within, I don't think we'll ever get there. I don't think we'll ever be able to say with certainty that we need to reduce this, increase that for any significant period of time.
Right. It's very much like many biological systems where you can't say something is bad, get rid of it. It's bad in all places. It's not. It sounds like, from just this description, that black carbon in the right particle size, in the right form, in the right part of the atmosphere, helps white clouds to form, which can block incoming sunlight and cool the planet. And white clouds look beautiful. So it's not just an equation we can say black carbon bad.
Right.
Finally, flaring of natural gas. So it's also implicated even in the effort to flare natural gas. And I said in our previous discussion that flaring, you might think, well, flaring's better than just venting. Flaring is very poor combustion. It would cost the industry a lot to try and actually burn the waste methane. The methane they choose not to even bottle. There is so much natural gas being released that it's far more than what they choose to capture and bottle or channel into natural gas supply for residential and industry uses. There is so much methane. They try and flare it, which means ignite it, but it is not very good. And for them to spend the time to properly combust it just as a method of disposing it would impose an extra cost into the system, which they're obviously not eager to do. But I did not understand that flaring, even of natural gas, I think of natural gas as mostly odorless, colorless, and with no physical, very small molecules. But apparently it produces black carbon. I did not know that. Did you know that?
No.
And so the mysteries abound. Again, another look. I love using different charts because they come from different sources. They have different emphases. They raise different questions, and they keep me focused on how do I relate all of these facts here. So black carbon, a big source is natural resources, obviously wildfires and wetlands, agricultural burning, shipping. And we talked about shipping. And even though it's a small pie slice here, it seems to have a big effect on Arctic ice and glacial ice. Transportation, other domestic burning, that's heating and cooking obviously using biomass fuels. So it is not the case that using wood to cook your soup is better than using natural gas. They both produce something that you would want to keep track of that is classed as a greenhouse gas and has effects. And then up here, oil and gas sector and other industry waste. So quite a diverse set of activities that we do and that we depend on are involved. Your thoughts?
Again, when you dig beneath the surface, you discover that there's a lot going on here. Black carbon emissions, just to call it global black carbon emissions, doesn't mean much. But then you break it down into these several categories, and suddenly your attempts to manage black carbon emissions just fly out the window. What are you going to do? You're going to manage domestic burning. You're going to manage natural resources, wildfires and wetlands. You're going to manage other, which is a pretty big slice of this pie, by the way, other industry waste.
Right.
And transportation. Yeah, let's just not have people drive anymore.
Right. And the biggest one, the gray, the domestic burning and heating, that's mostly the forms of cooking and heating with wood and charcoal and collected plant life that is done in what we call the third world or developing countries. And what are you going to do? Go to every shanty, order them not to make dinner,
Right.
make a meal for their family. And what are you going to give them? Are you going to give them properly and safely piped or bottled natural gas? If you're going to do that, well, that's good. But who's going to pay for that?
Right. And that natural gas comes with a cost too, you know.
It does. And are you going to give them, or you're going to give them a rocket stove? And there are people who, and there's even NGOs that have made it one of their activities is to teach people how to make a rocket stove out of local materials. You can make it out of bricks, you can make it out of mud, you can make it out of stone. It's just a different form of stove. And they go in and they teach people who live in mud huts and dirt floor shanties how to make use of what little fuel they have. And gathering firewood is becoming harder and harder because it's all been gathered. And so this is useful. And a rocket stove made out of some mud and sticks and bits of wood and broken brick in a third world country will perform better than the way they're probably cooking and will result in less dirty air in their lungs. But it's labor. It's an NGO sending people out with an educational mission to get people to do it. That NGO is not very strongly supported. Most people think, why would you help people with a cook stove? It's just not easy to sell.
Right. In this country and throughout most of the overdeveloped world, or I mean the developed world, we just take these things for granted.
Mm-hmm.
And it's hard for us to imagine that somebody doesn't have air conditioning when they live in a hot place like the tropics and subtropics.
The alternative to teaching them how to make and use a rocket stove, the next best thing would be to give them bottled propane, but the environmental activists would never sanction that because that's evil gas. And the very environmental activist has just finished unhooking his or her perfectly good gas stove in New York or California and ordering an expensive induction stove to be able to say at their next cocktail party that they are wearing the hair shirt, now cooking badly on induction stove. And they're doing that. They made that change in their lives for the planet. However, that electricity has to be generated and transmitted in plants that use sulfur hexafluoride to prevent the heart. And that's 25,000 times more damaging than the CO2, the smaller amount of CO2 that might be released from successfully combusting the gas in the gas stove they've just thrown to the curb. It is full of ironies, Guy, full of tragic ironies that Aeschylus, the Greek poet and dramatist, might appreciate.
Yes, it's a mess. It's a bigger mess than most people can even imagine. And again, we're just scratching the surface.
We really are. And so here is a map. They're able to map. Again, we have the sensors now. They're able to map black carbon on the ground in the Arctic. Ships emitted an estimated 67,000 tons of black carbon worldwide. So this next slide is really just talking about the very significant impact of what is one of the smallest pie slices in the data on the left.
Right.
So it's a small pie slice, but it has a big effect on something that really matters, which is the cryosphere, the ice at the top of the planet.
Yeah, this is the factor over which we have the least control that could cause the extinction of our species and therefore all life on Earth. An ice-free Arctic Ocean will, I'm relatively certain, be our demise. What are we going to do about that?
I agree. And already it's trending in that direction. You have been tracking the scientists who track this. They've made predictions about when we will see an ice-free summer, which we'll see first. Year-round ice-free is too horrible to contemplate, but even just an ice-free summer, am I right, is a milestone that has been predicted a couple of rounds already and has not, thankfully, happened. Have I got that right?
Absolutely. James Anderson, the Harvard atmospheric scientist, famous for discovering the link between chlorofluorocarbons and the Antarctic ozone hole, said, and this was in Forbes on January 15th, 2018. So more than 4 years ago, quote, the chance there will be permanent ice in the Arctic after 2022 is essentially zero, end quote. Well, here we are. It's 2024 last time I checked. And Jennifer McKinnon at the Scripps Institution in the University of California, San Diego, indicated that it'd be a year earlier than that. So these are renowned, intelligent people who have spent their lives studying these issues, and they got it wrong, fortunately for all of us.
Indeed. And so you are not the only one who's made predictions that sound dire and then had them not come true yet. And notice I said the word yet. Scientists who are as concerned as you are about Arctic ice have made some predictions based on what they see, based on their data, their honest predictions. Nobody's done anything. I mean, what's interesting is when they've made these predictions, nobody's done anything about it. The predictions have come and gone, and still nobody's doing anything about it. The only thing that I see being done about the Arctic and its diminishing ice is a nice sardonic smile on the faces of the Russian and international oil companies as they contemplate easier year-round access or almost year-round access to the myriad fossil fuel resources of that region, offshore oil, offshore methane, nearshore oil and methane, and the ability to now extract that at a much lower cost than if it were encased in 8 feet of thick ice. That's what I see as a consequence of diminishing ice.
That's the human response, though, isn't it?
It is.
Got to find the good and the bad. Oh, look, we can get more natural gas from the Arctic.
And so here at the end, we see that our activities around fossil fuels in this hydrocarbon age, we are not just doing one thing. We are not just even doing 2 or 3 or 5 things. Our civilization is, and just in the gases that I've covered here, which is, again, scratching the surface, we have covered just about every segment and factor of industrial life, both for individuals and the way they consume and live, and for industries, the extraction industries, and everything we do. I mean, you might think that what you do is just you eat food, you shop for food, and you drive a car. But everything, the building materials, the structural materials that your house is made of, that the roads are made of, that the chemicals that and processes that generated the food you eat and the electricity you consume, have all generated the greenhouse gases that we've been talking about. Where would you apply? Which hair shirt do you want to wear that's going to magically make all of these go away? There isn't one. That's my message from this.
Yes, absolutely. We have managed to, and I don't mean you and me, and I don't mean the typical person listening or watching. We have managed to put ourselves into a situation that's truly horrible. And I don't see any way out.
When you go to Mexico and you see how the Aztecs and the Mayans were dependent on various forms of very evolved aquaculture, digging canals and I forget what they were called. There's a name for them, a specialized kind of creating small islands for growing crops that was a form of irrigation. And they created complexity at a certain degree. And when that complexity suffered insults to its continuity from the environment, such that it collapsed, it became impossible to sustain. I think what some people who are still theorizing about why Mayan society and Aztec society came under pressure. It was local and regional climatological change in the water cycle and in other cycles that brought about the pressure that caused their degree of complexity to collapse. We've created complexity orders and orders of magnitude more complex and deep and wide that we are dependent upon. And there's both resiliency in that, in this complexity. We can make substitutions. When we talk about moving gasoline-powered vehicles to be electrically powered, that's a substitution, and it's quite a profound one, and it's already underway on some scale. But we then need substitutions for how we generate that electrical power. And we find that generating electrical power, we're using various very toxic, completely man-made, high-tech miracle chemicals that have a horrifying effect in the climate to generate that electricity. So no substitution so far that we've talked about is the magic one that is free of climate impacts. That's another more complicated way of saying the same lesson. Guy, do you have any closing comments?
There's no such thing as a free lunch. We keep looking, we keep seeking, we keep searching for the silver bullet, as it were, to get us from A to B without further dirtying our planet. It's not there.
It's very hard. So we close with our now regular last slide, this post-carbon, zero-emission civilization in a planet that is somehow going to be held back from blowing past 2 degrees and even 3 degrees. I just saw something that Henry Chu, the former Department of Energy head, I think he has won a Nobel Prize. He's a physicist. He is interviewed recently, last 3 months, Guy, I don't know if you've seen it. He says it's already baked in. We're going to blow past 3 degrees. So here's a mainstream person who was once the Secretary of Energy. Openly, he just said it's happening. It's not even stoppable now. Have you seen that or heard that?
No, I have not.
And so that was bracing at one level, but also refreshingly realistic to hear him say that, because I believe that. It would be
Absolutely.
a miracle. It would be a miracle if it stops at 3 degrees.
Absolutely. I mean, we're already past 2, according to governments in the world. So 3, sure, certainly seems like that could happen next Tuesday or whatever. But yes, already the ongoing rate of environmental change is horrific. And I don't see anybody talking about slowing that down.
I also, just thinking of the charts, some of the charts we've looked at that show the slope downwards that we're going to achieve through various cuts and in various scenarios that we get to net zero, and how that's going to, if we just do that by 2030, we can hold it at 1.5. Some people are still believing 1.5 degrees. Some people are believing at 2 degrees, whatever. I've discovered just in life in an apartment that trying to figure out with a thermostat. If the thermostat says it's 68 degrees and you're uncomfortably cool, and you turn it up by 2 degrees, I can guarantee that in a couple hours, someone in your family is going to be saying it's too hot, and turn it down. And then they're going to go to the thermostat and turn it down. If you can't even regulate, just think about your family living in with more than one other person or even just yourself, how difficult it is to just control the temperature in your apartment or house. And we think the way these environmental activists and policy people talk, it's as if there's some giant thermostat they think they're going to manage and just set it at 2 degrees Celsius higher than what we've got, and somehow it won't, it'll control it like a thermostat supposedly controls things. The Earth doesn't behave that way.
No, the Earth does not behave the way we want. And I'm not even sure whatever that means, that we agree on what we want.
And we speak, though, they speak as if there's some giant thermostatic dial that they're going to put a stop on that dial so it can't be turned past 2 degrees hotter than it is now. And I'm like, good luck. And they think they have a recipe for all the things we have to do to stop the actual temperature from swinging past where that thermostat is set. And I'm like, just try controlling the temperature in an apartment with 3 other people around. Just give that a whirl and get back to me.
And try to convince all 8 billion plus people on the planet what the desirable temperature is.
Yes, and that they have to make some of them have to make some sort of sacrifice to achieve this desired temperature.
What?
You'll find yourself out on your tuchus and told to take a hike.
Mm-hmm.
All right, sir. We've done enough domage for today, enough dommage. And again, we're just the messengers. I'm just doing lay research here, inspired by the thoroughness that I see Dr. Guy McPherson relaying to us, the scientific findings of many hundreds of scientists, all working diligently to try and uncover the facts and the truth about what is behaving on this planet, what is causing what. And it is an exceedingly complicated picture. But as a layperson, if you are interested in this stuff, all the research I've done has been just using normal search on Google and DuckDuckGo and other search engines. And you just have to start drilling into it yourself and try and find the answer that helps you understand what to do and how to think about what to do in this situation.
It's not that challenging, but it does require some effort.
Some effort and some critical thinking. And with that, I think we will declare a close for today and wait for next week with more surprises and interesting findings.
Until then, folks, thanks for staying tuned.
Be well.